Today, we're talking about the Pitot-Static System in aircraft, which is vital for determining the aircraft's speed, altitude, and its vertical speed. It powers three essential instruments: the airspeed indicator, the altimeter, and the vertical speed indicator. Understanding how the system works and what can go wrong is key to safe flying. The Pitot-Static System has two main components, the pitot tube and the static port, and both are carefully positioned on the aircraft to collect accurate data. A pitot tube is a small metal tube with an open end facing forward into the airflow. But they're not all the same shape. Some are cylindrical, but others may have a more of a flat or blade-like design, which makes them more streamlined. No matter the shape, the pitot tube is always mounted in a spot where it can capture undisturbed airflow, like on the wing or the fuselage. The pitot tube captures ram air pressure by facing directly into the relative wind. This pressure is created as air is forced into the pitot intake when the aircraft moves forward. As the plane speeds up, more air flows into the tube, increasing the pressure. This pressure is used to measure airspeed. You might also come across the term dynamic pressure. Here's what it means. Dynamic pressure is the difference between ram air pressure and static pressure. Ram air pressure is the total pressure, which includes both static pressure, the surrounding air pressure, and dynamic pressure caused by the aircraft's movement. The faster the plane moves, the higher the dynamic pressure. By subtracting static pressure from ram air pressure, we can calculate dynamic pressure, which helps us determine the aircraft's speed. The static port is a small, flat opening on the aircraft's fuselage, positioned where it won't be influenced by the aircraft's motion or dynamic pressure. It measures the static pressure or the ambient pressure of the surrounding air that isn't affected by the relative wind or ram air. Ambient or static pressure is the natural pressure of the air at the aircraft's current altitude. This pressure exists regardless of whether the aircraft is moving or stationary, and decreases as the aircraft climbs higher into thinner air. The static ports measure this air pressure, which is critical for determining altitude and rate of climb or descent. There are three main instruments that rely on the Pitot-Static System. First, the Airspeed Indicator, ASI. It uses the dynamic pressure from the pitot tube and static pressure from the static port to show the aircraft's speed. Then there's the altimeter. This one only uses static pressure from the static port to display the aircraft's altitude. And lastly, the vertical speed indicator, VSI. It also uses static pressure, but it looks at how the pressure changes over time to show the rate of climb or descent. Let's break down the mechanisms of these instruments, starting with the airspeed indicator. In the early days of aviation, airspeed indicators were much simpler. Some aircraft used devices mounted on the wing strut, featuring a plate that faced directly into the airflow. As the aircraft moved through the air, the pressure from the airflow hitting the plate was used to determine the aircraft's speed. While these early devices were not as precise as modern instruments, they gave pilots a basic idea of their airspeed. Modern airspeed indicators are much more sophisticated. The airspeed indicator works by comparing two types of pressure: dynamic pressure from the pitot tube and static pressure from the static port. The difference between these pressures gives us the aircraft's speed. As the aircraft moves, dynamic pressure increases with speed caused by the aircraft moving through the air. Static pressure, on the other hand, stays constant at a given altitude, regardless of the aircraft's speed. The airspeed indicator responds to the difference in these pressures and converts it into a speed reading. The greater the difference, the faster the aircraft is moving, giving us an accurate speed reading. Inside the airspeed indicator, there's a diaphragm, which is a flexible, sealed chamber. One side of the diaphragm is connected to the pitot tube, so it receives the dynamic pressure as the aircraft moves through the air. The other side of the diaphragm is exposed to the static pressure from the static port. The difference between these pressures causes the diaphragm to expand or contract, and mechanical linkages inside the instrument respond to this movement, indicating the aircraft's speed on the display. Remember, the ram air pressure, which comes from the pitot tube, includes both dynamic and static pressure. This is why it is called total pressure. Inside the airspeed indicator, the static pressure from the pitot tube inside the diaphragm and the static pressure from the static port outside the diaphragm cancel each other out. This leaves only the dynamic pressure, which is then used to determine the aircraft's speed. As the dynamic pressure increases with the aircraft's speed, it pushes against the diaphragm, causing it to expand. Since the static pressure remains constant, the difference between the two pressures causes the diaphragm to move. This movement of the diaphragm is linked to a system of mechanical linkages that translate the diaphragm's motion into rotational movement. The linkages move a needle across a calibrated scale on the airspeed indicator, which is marked with airspeed values. The needle points to the aircraft's speed based on the pressure difference. Now let's talk about the altimeter, another crucial instrument powered by the Pitot-Static System. The altimeter is responsible for measuring the aircraft's altitude by using changes in static pressure as the aircraft climbs or descends. So how does it work? The altimeter works by measuring the static or ambient pressure around the aircraft. As the aircraft climbs, it moves into thinner air and the static pressure decreases. As the aircraft descends, it moves into denser air and the static pressure increases. This change in static pressure is what the altimeter uses to determine the aircraft's altitude. Here's where the mechanical part comes in. Inside the altimeter, there's a sealed, sensitive diaphragm called an aneroid capsule, which contains a precise amount of air sealed inside it. The static pressure is directed only into the case. When the aircraft climbs, the surrounding static pressure decreases, causing the air inside the capsule to expand, just like a balloon. When the aircraft descends, the static pressure increases, and the diaphragm contracts due to the higher pressure surrounding it. This movement of the diaphragm is then connected to a system of gears and mechanical linkages. As the diaphragm moves, it drives a needle across a calibrated dial, which is marked with altitude readings. The gears convert the diaphragm's expansion and contraction into a readable altitude measurement for pilots. Now let's dive into the vertical speed indicator, or VSI, which shows the rate at which the aircraft is climbing or descending. This is a crucial instrument for understanding how quickly you're gaining or losing altitude, and it's important for safe flight operations. The VSI works by measuring the rate of change in static pressure. As the aircraft climbs or descends, the static pressure around it changes. When the aircraft climbs, the ambient or static pressure decreases, and when it descends, this pressure increases. The vertical speed indicator uses this change in static pressure to show how fast the aircraft is climbing or descending, measured in feet per minute. Here's how the VSI works in detail. Inside the vertical speed indicator, or VSI, the diaphragm is directly connected to the static port. As the aircraft changes altitude, the static pressure inside the diaphragm changes, causing the diaphragm to expand or contract in response. But here's the thing. The diaphragm doesn't react immediately to these changes because of the calibrated leak. This leak is a small, controlled opening connected to the case of the vertical speed indicator, not the diaphragm. It lets air enter the case slowly, which affects the pressure around the diaphragm, but not inside it. So when the aircraft climbs or descends, the static pressure inside the diaphragm changes immediately. But because of the calibrated leak, the pressure inside the case changes more slowly. This creates a delay. Now there's a pressure difference between the static pressure inside the diaphragm and the static pressure outside the diaphragm in the case. This causes the diaphragm to continue expanding or contracting until the pressure inside the case catches up with the static pressure inside the diaphragm. The faster the aircraft climbs or descends, the greater the pressure difference between the diaphragm and the inside of the case. This causes the diaphragm to expand or contract more, making the VSI needle move further up or down, which shows a higher rate of climb or descent. Once the pressures inside the diaphragm and the case eventually equalize, the VSI needle returns to zero, showing no climb or descent, just level flight with no change in altitude. The calibrated leak also prevents the VSI needle from reacting too quickly to brief changes in pressure. It acts as a time delay, smoothing out the needle's movement and giving a more stable, accurate reading of the aircraft's vertical speed. That's why the VSI doesn't show immediate changes in altitude, but gives a more reliable indication of the rate of climb or descent. Like any system, the Pitot-Static system can fail, and when it does, it can seriously affect your instruments. Let's talk about two types of failures: mechanical failure and blockage of the tubes or ports. Mechanical failures are relatively rare, but can occur. For example, a broken airspeed indicator could happen due to internal issues in the instrument itself. If the static pressure line is damaged, instruments relying on static pressure, like the altimeter or vertical speed indicator, may give inaccurate readings. Now let's talk about blockages, which can happen during flight due to things like icing, insects, dirt, or other debris getting into the pitot tube or static port. Blockages can cause issues with multiple instruments that rely on the Pitot-Static system, and it's important to understand how each one behaves. First, let's discuss what happens if the pitot tube becomes blocked. A blockage in the pitot tube only affects the airspeed indicator. When the pitot tube is blocked, if the aircraft is stationary, the airspeed indicator will read 0 because no air is flowing into the pitot tube. If the aircraft is in motion, the airspeed indicator will hold the last airspeed it was showing before the blockage occurred. So even though the aircraft is still moving, the airspeed indicator will continue to display the same airspeed as when the blockage happened, meaning the reading becomes inaccurate. Now, if there's a blockage in the static port, things get more complicated. A blocked static port affects not just the altimeter and vertical speed indicator, but also the airspeed indicator. Here's how. The altimeter will freeze at the altitude where the static port becomes blocked, so it won't show any changes in altitude, and it will stay stuck at whatever altitude it was reading when the blockage happened. The vertical speed indicator will show a constant climb or descent, depending on the pressure at the time of blockage. For example, if the aircraft was climbing when the static port got blocked, the VSI will keep showing a climb, even if the aircraft is no longer changing altitude. The airspeed indicator, although connected to the pitot tube, also relies on the static pressure to give the correct airspeed. If the static port is blocked, the airspeed indicator can't get accurate static pressure data, which causes it to display incorrect airspeeds. Here's how. If the aircraft climbs after the blockage, the airspeed indicator will display a lower airspeed than actual because it's using static pressure that corresponds to a lower altitude. If the aircraft descends after the blockage, the airspeed indicator will show a higher airspeed than actual because the static pressure it's using corresponds to a higher altitude than the aircraft's current altitude. So, with a blocked static port, the airspeed indicator shows a false airspeed based on incorrect static pressure. The altimeter freezes at the altitude where the blockage occurred, and the vertical speed indicator shows a constant speed or descent depending on when the blockage happened. This is why it's so important to be aware of the potential for blockages in these systems and to know how each instrument will behave when there's a blockage. Understanding these issues helps ensure that you can troubleshoot and maintain situational awareness if any of the instruments start behaving unpredictably during flight. Let's talk about pilot actions during pitot-static failures and how to handle them effectively. First, if your primary static port gets blocked, the alternate static source becomes an important backup. So, what is the alternate static source? It's an alternative way for your pitot-static instruments to access static pressure when the primary static port is blocked. In most aircraft, this source draws air from inside the cockpit instead of the external static port. In an unpressurized aircraft, the air inside the cockpit is almost the same as the outside air. However, it's not identical. There's usually a slight difference in pressure between the inside and the outside of the aircraft due to airflow and other factors. This small difference can cause minor errors in instruments, but they're usually small enough to manage without affecting safe flight. When you activate the alternate static source, your instrument might show slightly inaccurate readings. The altimeter could read a little higher than your actual altitude. The vertical speed indicator might show a minor climb or descent when you're level. The airspeed indicator might read slightly faster than your true airspeed. These discrepancies are something to be aware of, but they won't drastically affect your ability to fly. The important thing is to cross-check with other instruments and maintain situational awareness. Now, what else can you do if your static system or pitot tube is blocked? For example, what if your airspeed indicator becomes unreliable because of a pitot tube blockage? This is where additional actions come into play. If your aircraft is equipped with GPS, it can be a helpful tool. While it doesn't give you airspeed, it does provide ground speed. Ground speed isn't the same as airspeed, but it can help you gauge how fast you're moving relative to the ground. By comparing your GPS ground speed to your expected performance, you can get a sense of whether you're maintaining safe speeds. Additionally, rely on instruments that don't depend on the pitot-static system, like your attitude indicator and heading indicator. These remain reliable and can help you maintain control. Focus on keeping straight and level, steady climbs or descents, or holding your heading as required. If you're flying in visual and meteorological conditions, VMC, use visual references outside the cockpit. Look for landmarks, monitor your altitude changes visually, and stay aware of your surroundings to avoid terrain and obstacles. In low visibility and instrument meteorological conditions, IMC, it is critical to follow your training for partial panel flying. Inform Air Traffic Control, ATC, about your situation as soon as possible. They can provide vectors or altitude guidance to help you maintain safe flight. Finally, always refer to your emergency checklist. Following the checklist ensures you don't miss any important steps and helps you stay calm and focused during the situation. With these actions, you'll be well equipped to manage a pitot-static failure safely and effectively. Understanding the pitot-static system is an essential part of flying safely. These systems give us the critical flight data we rely on, so knowing how they work and how to handle any potential failures is vital. Whether it's a pitot tube blockage, a static port issue, or even a mechanical problem, the most important thing is to stay calm. recognize the symptoms, and use your backup systems or alternative methods to keep the aircraft under control. If you found this video helpful, make sure you hit the like button, leave a comment, and share it with anyone who might find it useful. I'd love to hear your thoughts and suggestions for future topics in the comments below. Also, if you can confidently answer the questions in the description below, you're well on your way to mastering the Pitot-Static System and understanding its key components. Thanks for watching, and remember, your knowledge of systems like the Pitot-Static System is what keeps you prepared for whatever challenges you might face in the sky. Safe flying.